Okay, today we're going to be studying some collision theory. Collision theory is also part of the kinetic molecular theory, and what it says is that particles are just moving around and they're hitting each other, they're colliding, and in those collisions they're transferring energy to one another. And the only way, the important thing about collision theory is that it says that reactions only occur by colliding. So two particles will come together, they'll hit each other in a specific way with a certain amount of energy, and they can react. Now we have an example of this right here. So we have particles A and particles B coming together, and they hit each other. They hit each other and they form this kind of weird, little bit different activated, what we call an activated complex. Okay, this activated complex is extremely unstable, and it's very, very short-lived. It doesn't last very long. It's unstable and then breaks apart, and then we get what we see here is our new products. So we have reactants A and B coming together, they hit each other, and they'll make products AB. Okay, now we're going to look at a few different things that can affect reactions. So the first one is the effect of concentration. It says here, the greater the amount of particles, then the more collisions you'll have per second. Higher concentrations mean higher reaction rates. So again, what happens here is particles will come together, they'll hit each other, they'll form this activated complex, and they'll make products. So reactants come together, hit each other, activated complex, products. Now this whole reaction depends on this A coming together and hitting B, and there's not a lot of chance. If these things are just flying around randomly, there's not a lot of chance for it to come into contact and actually hit B. If these two things were just moving around randomly, they're not going to be hitting each other very likely. But what we can see is if we increase the concentration, so right now we have 3 particles of A and 3 particles of B. Now if we had 3 particles of them moving all around every single direction, and 3 particles of B moving all around in every single direction in this container here, then there's a higher probability that they'll come into contact and they'll hit. And more collisions mean a higher reaction rate. Now let's look at the effect of temperature on a reaction. So the higher the temperature, the faster particles are moving, and the more collisions you'll have per second again. But also, in addition to this, not only will you'll have more collisions per second, you'll have collisions with more energy. And if you have collisions with more energy, they will be more successful. So higher temperatures will then equate to higher reaction rates. So let's take a look at this reaction right here. So again, we have A and B coming together, and they form this kind of weird complex. Now if they didn't have enough energy, this is the kind of thing that would happen. A and B would come together, they hit each other, but they didn't have enough energy, and so they just split apart. So what we see here is they did hit, there was a collision that took place, but they split back apart because there was not enough energy. Okay, and this is really, really important. You can have collisions happening all day long, but unless they're collisions with enough energy or enough kinetic energy, then you're not going to have a reaction. Okay, so this is effects of temperature works on two levels. The first one being you'll have more collisions, and the second one, you have more energy in the collision, and that is what increases the reaction rate. More successful collisions. Now let's talk about some enthalpy changes in chemical reactions. So again, enthalpy is the total amount of energy that is within a system. The change in enthalpy can be calculated by knowing the total enthalpy of the products minus the total enthalpy of the reactants. So let's take a quick little graph of this. So if on the y-axis we have something like energy in a system, and here we have time, or in other words, reaction proceeds, and if you had this side right here, so we have the reactants, if this was a reactant, it has a certain amount of energy. Okay, it has a certain amount of energy. So right here, this number right here, so if I were to draw right like this number would be our H initial. It is the enthalpy that we have at the start, okay, from right here to here. Now whether it goes up or whether it goes down is, it depends on the type of reaction, whether it's exothermic or endothermic. So we're going to have this one requiring energy, and it's going to go up to something like that. So what we see here is that this one had to go like this, and now this is the enthalpy of the products. So in order to find how much it changed, well, you would find the enthalpy of the final minus the enthalpy of the initial, or the enthalpy of the products minus the enthalpy of the reactants. And this right here, this distance, or this number, is going to equal your delta H, because this distance right here is just the difference between products and reactants, or H final minus H initial. And that's going to equal your change in enthalpy. Okay. Now, since this went up, okay, this went up, delta H right here is going to be a positive number, or in other words, this really big number minus this little small number, it's going to be a positive number here. Okay. So this is what enthalpy is, and this is how enthalpy can change. Okay. So the enthalpy in the reactants, or the amount of energy in the reactants, is dependent on what kind of the reactants, what are the reactants made, or what are the reactants and the properties of the reactants. And the enthalpy of the products, again, depends on those specific types of molecules, and they each have a very specific type of enthalpy. And for here we show that the reactants have an enthalpy down here, and the products have an enthalpy up here. So there's going to be a big change in enthalpy if this when this reaction proceeds. Now let's talk about a few different types of reactions. So the first one we're going to talk about is an endothermic reaction. Now an endothermic reaction is when the enthalpy of the products is greater than the enthalpy of the reactants, or in other words, H products is greater than H reactants. Now if we were to have a formula or a balanced equation of this, it would look something like this. Reactants plus energy is going to be making products. So energy is going to be on the reactant side. And as a result of that, the surroundings are going to feel cooler because energy was absorbed in from the surroundings. So the reactants are combining with energy. The energy is coming from the surroundings, and it's going to be making products. And since the reactants are absorbing all the energy from around itself, the surroundings are going to feel much, much cooler, and therefore it has enough energy to form products. So if we have reactants, something like way down here, it's going to be absorbing energy, or therefore increasing its enthalpy, and it's going to come up here and form some products. So again, this is going to be your reactants, and this is going to be your products. And this is going to be your change in enthalpy. Okay, so reactants and products. And therefore, since we have this, our change in enthalpy for an endothermic reaction is going to be a positive number. In other words, Mr. Lum symbol. Positive. It's going to be positive. Okay, and that makes sense. It's going up, and therefore it's going to be positive. Or in other words, if we just plug this into our formula of delta H equals our H products minus H reactants. Okay, bigger number minus a smaller number. Now let's talk about exothermic reactions. Okay, now exothermic reactions are in many ways opposite of endothermic reactions. Instead of having the enthalpy of products greater than, exothermic reactions have enthalpy that is less than the enthalpy of the reactants. So we can see this, or we can also write this as H products is less than H reactants. Or in other words, energy is going to be on the product side. So if enthalpy of the reactants is going to be a bigger number than the enthalpy of products, what we're going to have is our enthalpy of the reactants is going to start way up here, and enthalpy of products is less than enthalpy of reactants. It's going to start to fall and come down here. So again, H products, which is here, is less than H reactants. Now, since the energy is on the product side, the reactants are going to lose a whole bunch of energy in order to become products. So since they're losing a whole bunch of energy, that energy is going to be released into the surroundings, and therefore the surroundings are going to feel warm. Energy is exiting the reaction, or exiting the reactants, and therefore the surroundings are going to feel warm because energy was released into the surroundings. Now, when we graph this, since H products is a smaller number than H reactants, this is what our delta H is going to look like. Delta H is going to look something like this. Okay, where it's going to go down. And since it's products minus reactants, again, delta H is going to equal H products minus H reactants, it's going to be a negative number. Delta H is a negative number. Or in other words, it's negative. Okay, and that makes sense because what we see is that it starts up here and it's going down, and so therefore delta H is going to be a negative number. Okay, so what I would like you to do is read your book in Hebden and review some of these ideas about exothermic reactions and take a quick review. Okay? Bye-bye.